Our next speaker is Abdul Ayare from Mentor Graphics, one of our sponsors today. Abdul is an application engineer for formal verification, clock domain crossing, and low power verification. He received his doctor in formal verification at the University of Freiburg and worked for Micronas GmbH before joining Mentor Graphics. The title of his talk is Formal is the New Normal.
Thanks for the invitation. So my name is Abdul Ayare. I'm working since 2008 at Mentor. I have been working with design teams across Europe and helping them to adopt formal verification. I'm pleased to be with you today and to share some of the trends that I'm seeing in the industry that are leading to increased use of formal verification. Across industry, we see design teams feel squeezed by time to market and increase of design complexity. They have limited resource and face numerous challenges that slow them down. From the other side, we can also not afford to take any shortcuts. Otherwise, they run the risk of finding bugs in silicon that leave them behind the competition. So in the most of customers get enabled get their verification done using simulation alone. Today we are seeing customer coming back to us and asking for more tools to get their job done. They are actually not doing less simulation. In contrast, simulation is still growing. What we see is that in one side, more verification is pushed down to emulation at system level and upstream to pushed upstream to formal verification at the block level. So what we are witnessing is that formal verification is the use of formal verification and the ABA spending on formal is in the rise across industry. The formal verification target, the formal verification market is about 32% in the last 5 years, and this year is expected to top the 100 million mark, which is actually very good news. The formal verification is actually a very this is a research. This is known to be a very challenging research area, and the research community is very active on this in this topic. This growth means for us actually that for your company, large industry leaders are expanding their use of formal verification, and other has to follow suit to be competitive. For you and me or I, this is means there is a lot increased demand on verification engineers with verification skills and experience. So I want just here go over three main factors that I see that are essential in this growth and explain them a little bit in details. So the first one is actually about the core technology itself. This is used in most all commercial tools. Over the last 25 years, just as we have seen a lot of advancement in other areas like mobile technology, there is there has also continuous research breakthroughs in formal verification. Formal verification is research, is an area where with very exciting research challenges, and the research community is actually very active. As a result, we see today, as a result of these research advances, we see that commercial tools have a lot of improvement in performance. So if we consider, for example, the earlier 19, the first model checker built based on symbolic model checker based on BDD, that was a very exciting stuff, and small circuits was completely proven to be correct using this model checker. But the evolution was ongoing actually, and a lot of good work was done in different disciplines. For example, in the abstraction, where people have tried to find ways to make a search space smaller and to accelerate the proof engines. There is also for the model checking algorithm itself a lot of improvement. If we think about the interpolation from Mr. Macmillan, or the bound model checking from Ed Clark in the 2003 or 2002, these are actually new technology that helps model checker to be more performant. So model checker use in the behalf under the hood SAT solver, and on SAT solver also there is a lot of good work done in the academical world. If we take, for example, the chat solver, or the chat solver is a poorly academic tool developed at Princeton in US, and this tool is actually used in most available commercial tools, and this is making them very successful. What we have seen also in the last 3 years is a new algorithm based on induction. Is called AC3. It's based on induction and combined induction and SAT solver. And this new algorithm is actually behind the performance that we see today in commercial tools. Sorry. Yeah. Here, small details about IC3. It's actually about inductive proofs. As you remember from the school time, induction, if you can do proofs by induction, it's actually easy. If you cannot manage to do this by induction, then you need some auxiliary help. So auxiliary, some kind of help function or help facts that helps you. That is the same principle here. Inductive proofs are proofs that can be proven in the initial state in all the next states. If a property is provable, then it can be made stronger to be inductive. And the challenge here is how to make this proof stronger, how to make to find some auxiliary property so that the conjunction of these two things make your property stronger. This is the big challenge, but there is constructive ways how you can do that. And the way is actually to use some counterexample, negate them, minimize the counterexample, and so on. And in this construction, you can use a very clever SAT solver. The main benefit of using induction in model checking is that you are not forced to use model checking, because bounded model checking forces you to unroll the transition state. Induction is always talking about it's local, it's talking about two time points. This makes actually the proofs the memory consumption very slow, very short or low, and runtime actually also very good. As usual, there is some cases where boundary model checking is still superior. So that is always the case. So at Mentor, we are working with different universities. We have in our Questa formal research, we have two researchers that are working with University of Colorado. It's Mr. Bradley, who has invented the IC3 algorithm, and Mr. Sorensen from University Gothenburg. They are a member of two teams, and these two teams together won gold in half of the category and silver in the other half in the last model checking competition last year, in October last year. So in Questa Formula, we make available all this breakthrough technology and make this available for our customer to be used in their daily business. So this is the first factor. It's about the core technology, which is actually still ongoing. The second one is about ease of use. If you go back to the first days of form verification or usage of form verification in the hardware community, that was not actually too much present, ease of use. And today we can speak about formal ease of use. So there is different types of tools that are based on form verification. The first one is what we call fully automatic formal. This is an application where actually when you run this application, you don't have the feeling that you are running a formal tool. This, for example, club domain crossings, this property generation or reachability of code coverage, and so on, or X-checking. So the main advantage of this is that the user does not have to have any verification skills. So this is actually push button technology. The next one is where the user has not provided the assertions, like the first one, but has to provide some kind of input telling the tool what kind of application he wants to run. So the first application is the tool knows about the application itself. The second is the tool actually get help from the designer and from the verification engineer specifying whatever he wants to achieve, proving that design constraints are consistent or connectivity checking, standard protocol, whatever. So some help is needed from the user just in terms of providing or specifying the task that has to be achieved. But even here, actually, formal skills are not needed. If we go higher, so we see more skills are needed, in particular for property checking, where users write their own assertion to target specific requirements. Can be requirements for the system level, can be for subsystem level, can be for different structures, implementation structure that are using in the design, and so on. And if we go further, we found also architecture verification, like cache currency and system deadlock. For this kind of application, more skills is needed, and but this is actually used. It's just how to say is manageable. So I want to go over this three types of examples and show how this works in practice. I will start with the automatic formal application. So I picked up the X-checking. So actually eliminating X in your designs is not an option. It's actually a must. The problem that we see is that designer, because of area, because of constraint, of timing constraints, they are leaving some storage elements not resetted, not explicitly resetted. In particular, databases which are dangerous. So they are not doing explicitly reset for that. And they are assuming that this storage element gets flushed out before getting sampled. The thing that makes this problem more harder is that, for example, if you consider simulation, sometimes you are dealing with, you have the situation where you are dealing with X, but in reality there is no X there. It's only because the simulation is dealing with an X pessimist situation. In different scenario, you have this, you see solid value for some signals, but actually the simulator is optimist and making solid value, known value, rather than to have X. This X optimism is actually very dangerous. So using this verification technique, it means you are verifying not what actually is happening in the silicon. And this is a very dangerous situation. In Mentor, we have a solution for this, one solution-based simulation and one solution-based formal. For formal, we are targeting subsystems, targeting block level. So we check the RTL for sources of X. Then we check the initialization steps for instances of X pessimism on X optimism. Then we generate assertions and check using the formal engine for X propagation. Here again, we need specific accurate semantic to handle this propagation. So the synthesis semantic will not fit here. Mediatek is a company which is designing big socks for multimedia. Is actually aware about X checking and have had a lot of coding style, and their designs are asked to follow this coding style strictly, these coding styles. And there is a lot of verification tools in use. Nevertheless, there is bug still found using these traditional verification tools. So they used X-check and found for different blocks about 10 bugs. The second application, which is fit to formal application, is actually SOC connectivity. So as we know, SOCs have a lot of processor, IP designs, a lot of connectivity, a lot of I/O mopsing. So actually, you have the number of connectivity are in order of thousands. So if you want to address them using simulations, then you have to write functional test cases to address them. This is a very big weakness. So the other thing is that you have to start late, because you have to wait that everything is there and the test engine environment is also there, and the different components in your sources are there. So this is actually something that you can do easily in continuous form. Okay, so it sounds a little bit strange because we are targeting the SOC, but actually formal verification can target the SOC, and for the assertion to be proven, we can black box whatever is not used there. So the user is asked to provide some input here in Excel format, in Excel sheet format, XML, whatever, and to tell the tool what is actually has to be connected and under which connections. So the tool will generate assertion and prove the assertion, provide an environment, debug environment for the verification. The verification engineer can fix the RTL or fix the input spec and make some iteration. So here actually if the Excel sheet is complete, you can also generate some kind of test plan for your connectivity, and you can get back annotated your test plan from the formal tool, and so that you can at any time check what are the assertions that get proven, what are that are exercised, and the assertions that for which that are not exercised so far because the components are not on the ship. So that is also something that you get for free. So Rockwell, one of the large industrial automation company, was using creating socks that are processor based with a lot of connectivity. They are asked to prove the connectivity due to safety integrity levels, level requirements there. So the socks, the socks has a large number of connectivity, and they cannot do this with with simulation. So they use Questa formula for this application, and in two different areas, in pin multiplexing and in block interconnectivity, and have good results. One particular thing is to mention here is for the SOC in question here, and that they have verified, the boating is placed in some external ROM, and they found out that there is two connectivity bugs with this ROM that prevented the ship actually to boot as expected. So that was actually a very dangerous error that was found using formula. One other thing is that they reported that they have a 10x time saving. The next one is actually the most known one is the property checking itself. This is if we go back in the first model checker in the hardware. This is what we were asked to do: write your assertion from the proof and generate the proofs or counterexamples. So you can write assertion yourself to address different requirements, proof assurance for safety critical application, or you can address coverage holes. So you can have a situation where you have a regression running for a long time, but something is very important, is not covered. So you can write your sequences and target these sequences as cover points or cover directives in the assertion in the formal tool. Also, another topic is post-silicon. You have failure in the silicon, so you don't know where this failure is coming from, in which part. So you can use formification to localize and to capture the error or the failed behavior of the design. So you can use the assertion on different levels in a black box way, where you are talking about interfaces, or you can also in white box way, where you can talk about your specific implementation, and even on the system level when you are writing some end-to-end requirements. Usually the language in use are the standard ones: PSL, system level assertion, OVL, sometimes vendor-specific libraries. So the usage of standard language makes sense because you want to reuse this assertion in different other tools, in different other techniques. So Oracle is actually one company which more or less matched this pyramid that I showed you before, and started with with connectivity, then had some experience with connectivity, extended the connectivity to property checking, make property checking at different level for some controller. I was able to run Formel for bug hunting, and even they have expertise captured from the verification done by Formel to as coding style or coding requirements for designing. So as a result, actually, they have found a lot of bugs earlier in the design process. So here, will be a paper in 2000, an edition paper in DDCon 2014 this year. The picture shows that actually there is a lot of bugs were found at the beginning of the process with Formel. So this gave them time to react to these bugs. Nevertheless, with the simulation, we still have found bugs because of the integration of the whole system. So another topic that is actually very essential is the integration of tools. So today, the usage of tools is actually complementary. So you can use Formel to complement results from the emulation, results from simulation. So the verification the Monitor Enterprise verification platform integrated different solutions and make it possible that this solution communicate in a straightforward way. So here is again one application, the coverage closure. In this coverage closure, you target the results of the simulation. You can identify the items that are not covered. You run your Formel tool and find out what is actually cannot be reached. You can exclude that from your simulation. You can also find proofs that these things can be reached. You have witnesses for that. From the witnesses, you can create test benches, and so on. You can actually enhance your verification environment. Microsoft is developing or has developed the biggest SOC in the world. Maybe this Xbox One, about 5 billion transistor. I was interested to see everything covered and use cover check. And what I can say in brief is that they achieved improvement of 10% using cover check. And they said that they have 4 months saved, 9 months saved. This is actually a very conservative estimation because they put 10 minutes to waive or exclude the coverage hole, which is actually not realistic. But nevertheless, this is still a huge number. So this paper will be presented in DAC 2000 this year, the next coming DAC. So to conclude, Formel adoption is increasing. It will be faster, smarter, stronger, more. We will have always better algorithms. The ease of use will increase, and the integration will not stop. So, maybe this is the reason why I'm...
Okay, thank you very much.
this way.
Any questions? Actually, they must have sit near the front, so... You're going to keep me fit.
Hi, Ashish Surbari, Imagination. You had this slide about Formel's adoption increasing to, 32% in 2013. And year by year, there's been an increase. And then you had another slide which said, there are 4 different models of Formel use. Do you have any insights into which category of Formel use has seen surge?
Yeah. Actually, I don't have the details, but I can guess that it's the automated solution.
Most, yeah, okay.
The automated solution that is giving this factor. In particular, the CDC staff is giving this factor.
So I'm Chris Brown from Broadcom. So you're talking about the X propagation. I think you said that Mentor will sell a simulation tool for X propagation.
Yes.
And a formal tool for X propagation. Which do I use?
Sorry?
Which should I use? You're telling me two tools.
Yeah. So, of course, so the one thing is you have to, for formal verification, you can address blocks, subsystems. You can go a little bit higher, but sometimes you can get stuck because the power engine will not give you decidable results. So what we can do, so there is some limits, so you cannot address the whole system level. The simulation is actually for the system level. So there is a simulation-based flow and works for the simulation. For things, for blocks for which you don't have any test case or that has any test bench that you can easily run, it's actually recommended to run X-check for that. So these two tools are complementary to each other.
Okay, so if I got a small block, you would recommend simulation, you'd say?
Yeah, I would say, for some subsystems, I will use Questa.
And just one final question, which is from online. It's referring to the case study at Rockwell Labs. The question was, an impressive number of bugs were found with formal so quick, but how many of those bugs were cosmetic? Were any of them severe bugs?
So about which one is the...
Rockwell Labs. You have to go a long way there, I think.
Yeah.
This is just a question about that. Do you know how many bugs were severe or how many were cosmetic?
Yeah, in the paper they are talking about some paper which was in maybe skipped to silicon. I don't have the number, but that was severe, some bugs which were severe to fine.
Okay.
So I don't have the numbers here, but one number.
Okay. So there's no more questions, so I think just thank you very much to Abdul. Thank you.